Hello everyone, welcome back to this week's algebraic graph theory seminar. This week we have Xiaohong Zhang to tell us about oriented Cayley graph with all eigenvalues being integer multiple of square root of delta.
Hello everyone, thank you for coming. So we're going to talk about oriented Cayley graphs. This is a joint work with Chris. This talk has two main parts. The first part is we get the characterization of such oriented Cayley graphs. The second part, we will see some of its applications in continuous quantum walk on oriented graphs. So to answer the first question, we will break it into two parts. We first find out what are the possible deltas. Then we find the characterization and see some examples to check how to use the characterization. First, what is an oriented graph? So it's just a simple digraph where between any two vertices, there is at most one arc between them. We cannot have some other ones. We can represent an oriented graph with a matrix. Here we are interested in 0, 1, minus 1 matrix. So we have an arc from 0 to 1. The 0, 1 entry is 1, and the 1, 0 entry is minus 1. There is no arcs between 0 to 2, so 0, 2 entry and 2, 0 entry are 0. It is a skew-symmetric matrix. So that's the more formal definition. Arc from A to B, we have the AB entry being 1. What is a Cayley graph? To define a Cayley graph, we need a group. So let G be a group, and we take a subset C of G such that the group identity is not in this subset C. Now to construct a group graph, we just assign a vertex to each group element. If say there are two group elements G and H, we have an arc going from G to H if and only if G HG inverse is in that subset C. It's called the connection set of this Cayley graph. In this talk, we will focus on abelian groups. So instead of using multiplication, we will have a summation. And this G inverse will just correspond to H minus G. So G inverse corresponds to minus G. Let's check some examples. So the group is the cyclic group of order 6. We have only one element in the set C. So any two elements, if they're different, if H minus G is 1, there is an arc from G to H. So for any I, there is an arc from vertex I to I plus 1. All the indices are modulo 6. Another example, we have the connection set has both 1 and 5. So we will have an arc going from 0 to 1 and 1 to 0. It's the same for each of them. Instead of doing this, we will just draw an edge. We have an undirected graph. Of course, it can also have something, have both edges and arcs. So this element 2 will create this oriented 3 cycle inside. This is we usually call it a mixed graph. How are the 3 types are determined by this connection set C. So if we negate all the elements in C and denote the resulting subset as minus C, the first one possibility is that the two sets are identical, just like this case. We will have an undirected graph. We just call it a Cayley graph. On the other extreme case, C and minus C are disjoint. In this case, we will have an oriented graph. Because, so if it means, if they are disjoint, it means if G minus H is in the connection set C, then H minus G is not in, so there is only one way. And this one corresponds to the case C and minus C overlap, but they are not identical. We will be focusing on these types of graphs. Let's repeat. Now we know what is an oriented Cayley graph. Let's repeat our question. We want to know what oriented Cayley graphs has all its eigenvalues being integer multiple square root delta. Delta must be negative here because the adjacency matrix we are using is skew-symmetric. So all the eigenvalues are pure imaginary. We will, so this negative sign will give us an I. So this question has its history. If we consider unoriented, just consider Cayley graphs and let delta equals 1, we are asking which Cayley graph has all its eigenvalues being integers. To answer this question, we needed to define an equivalence relation on this group G. So two group elements G and H are equivalent if and only if they generate the same cyclic subgroup. And Bridges and Mina answered this question in 1982. It said a Cayley graph has all its eigenvalues integers if and only if this connection set C is a union of the equivalent classes. Let's just check a quick example. So this, we have the group G is Z6. We can check, let's check which elements are equivalent. 1 and 5 are both generators of the group. So that's the only two. 2 and 4 are equivalent. 3 itself, there is also 0. So using this result, we just know directly that 6th cycle has all its eigenvalues being integers. That's so much strict. I like to use this result, it's immediate. Similarly for this Z8 one, 1, 3, 5, 7 are all the generators of the group. The equivalent class contains 4. It only has 4 itself. So it's a union of equivalent classes. And by the above result, we know this Cayley graph has only integer eigenvalues. So we want to check about oriented Cayley graphs. Let's try to start to check some examples first. Again, if we take this Z3 element, this is an equivalent class. They are generators, and 1 and 2 are negative with each other. To have an oriented Cayley graph, remember if G is inside, minus G must be outside. So we could take one of them, at most one of them. Let's just take 1. We will have an oriented 3 cycle. That's the skew-symmetric adjacency matrix. And it does work. Delta equals -3. Let's check more examples. So cyclic group of order 8. This is an equivalent class. They are all generators of the group. Again, negative pairs show up together. For each pair, we can, by the Bridges Mina result, we know all the eigenvalues are integers. So for each negative pair, we can take at most one of them. If we take 1 and 5, it works. Delta equals -1. If this is the only possibility, we can check when we take 1, 3, it also works. Delta equals -2. And that's all the possibilities to take, That's all the possibilities. If we ignore the case, we take 7 and 3, take the negative element. It just means all the arcs are reversed. One more examples. So yeah, before that, from the 2 examples, we check the deltas. So both -1 and -2 are divisors over 8. So are all the divisors achievable? Are non-divisors achievable? Let's check the example on 12. We know it's square-free divisors have -1, -2, -3, -6, but only -1 and -3 are achievable. So we will figure out which ones works later. So far, another question is that are these feasible deltas determined by the group order or something else? Let's check an cyclic group. So Z8 times Z4. We checked there are other examples, but all the achievable negative deltas are -1 and -2. It's the same as this cyclic case. So it's not determined by the group order. Now let's try answer this question in steps. For each group, what are the possible deltas? Then for each achievable delta, what's the condition on the connection set? So as the example suggests, it turns out the group order doesn't matter. It is for the feasible set of deltas, it's divisible. It's determined by the group exponent. The group exponent are the smallest positive integer, such that multiply any group element by this integer, we have 0. Here we are for abelian group, it's the same as saying N1 is the largest element order of G. Anyway, so delta is determined by the group exponent. And to check which deltas are realizable, we need to check the multiplicity of 2 as a factor of N1. So if N1 is a multiple of 8, and we know all the square-free divisors of N1 are realizable. If N1 is a multiple of 4 but not 8, we are taking the square-free divisors, but we can only take the odd one. 2 is a divisor. Some divisors multiplied by 2 is also a divisor, but it doesn't work. For other cases, which means N1 is an odd number, or it's just a multiple of 2. It's 2 multiplied an odd number. In this case, we still can only take the odd divisors, but not all of them. We can only take the ones being congruent to 1 modulo 4. Let's just check some quick example, like to get a feeling. So 40 is 8 times 5. The prime factors are 2, 5. Because it's a multiple of 8, we can take all of them at any of their product. So -2 - 5 - 10. And if N1 is 60, have 2 squared times 3 times 5. So in this case, we can only take the odd divisors. we will have a delta equals -3, -5, -15. Maybe just one more example. Check 15 equals 3 times 5. -3 is congruent to 1 modulo 4. -5 is congruent to -1 modulo 4, but their product works. So delta equals -3 at -15. -5 is not achievable. That's just some summary of these examples. Now, so for this list, we are only checking some negative deltas. If we take both positive and negative ones for the first two cases and take all the numbers in the third case, it will correspond to some number we will mention later. So to find out what deltas are realizable, we need some Galois theory. So assume we have a field K, and we have a larger field F contains K. We consider all the field automorphism of the big one, and we collect all the ones that fix all the elements in the small field. The connection of such automorphisms is called the Galois group of this field extension F over K. So we use this notation. So we have some field extension, and there is some Galois group here. We might have something in between. Turns out there is a nice relation between the field side and the group side. So draw it again. So base field K, large field F, there is a corresponding Galois group. If we assume we have a subfield of F, E1 that contains K, we will have a subgroup here. This subgroup corresponds to automorphisms with a big field that fix the bigger subfield E1. There is some, there is a one-to-one correspondence between subfields and subgroups, but the order is reversing. So we have a bigger subfield E2, there will be a smaller subgroup. More to that is the index of extension for E over K is equal to the index of the subgroup over in the original big Galois group. So that's the correspondence of extension degree and the subgroup index. Here, with the two fields we need to use here is, so our base field will be the rational field Q, and the bigger field is the cyclotomic field. Again, N1 is the exponent of the group, and zeta N1 is the primitive N1's root of unity. The role of root delta comes here. We consider a quadratic extension, the quadratic subfield of the cyclotomic field. So again, here we have the Galois group level Q. We might know that this is isomorphic to the multiplicative group of modulo N1. Back to here for the subgroup, so this extension index is 2. Degree, the extension degree is 2. We need to find a subgroup of this Zn1 that has a degree 2 index. Sorry. So we know how does this, if we check the factorization with the exponent N1, we know how does this multiplicative group look like. It can be factored like this, a direct product. So for all the prime part, they are cyclic and over even order. So each of them has a subgroup of index 2. For this one, it's a bit different. It's a direct product of a cyclic group of order 2 with a cyclic group of order 2 raised to m minus 2. When m is small enough, we can just check directly Z4 or Z2, or not go to there. So all of the collection of all these, the collection of subgroups of this group of index 2 are exactly the all those deltas we get here, including the positive and negative ones and all the doables one here. So we know which deltas are realizable, and the tool we use is some Galois theory. Here, let's try to check the characterization for each delta. Before that, let's introduce some symbol, the Legendre symbol. So P is a prime, and K is an integer. If this symbol is equal to Z, it has only 3 possible values, 1, -1, and 0. If P divides K, this value is 0. It's 1 if and only if it's a non-zero quadratic residue. What does this mean? It just means there exists some number x such that x is congruent to K modulo P. If there is no such x, it's a quadratic non-residue, then the value is -1. So we have been talking about subgroups of index 2. Our main characterization is to try to find this subgroup for each delta. So this is a more concrete way to get all the deltas. All these W's are either 0 or 1. And if like mentioned earlier, if the multiplicity of 2 is too small, so the W0 and W can only be 0. So we have a delta list. For each delta, we get we take elements in the multiplicative group of modulo n1, but we want the evaluation of it on this expression to be 1. So it's a subgroup of this group. Again, it's isomorphic to the Galois group of the cyclotomic field over rational field Q. Using this subgroup, we define an equivalence relation on the group G. We see 2 elements are delta related if there is an element K in the corresponding subgroup, such that multiply one element by K, we get the other. There is a special case for delta equals 1. What does that mean? For delta equals 1 means all the Wi's are 0. So it's like everything takes the exponential 0. So any number co-prime to n1 is still in this in the subgroup. In fact, H delta is the group, the big group itself. The index is just 1. It corresponds to the earlier result we mentioned by Bridges-Mina about when a Cayley graph has all the eigenvalues being integers. Remember earlier the characterization is the equivalent relation is that 2 elements are equivalent if and only if they generate the same subgroup. And it's equivalent to this correct. It's the same to this equivalent relation. So 2 elements, assume G is a group of exponent n1. 2 elements are equivalent if and only if K times H is equal to G for some K in ZA1 for their co-prime. So we obtain the result again. For other deltas, if delta is not 0, 1, we have a quadratic extension. In particular, if we want to get, for oriented Cayley graph, the deltas must be negative. So for this, we write delta as a product of the different primes. And again, there is a corresponding subgroup. This square root is achievable if and only if this is an odd number. So this WI is just mean whether we are taking the PI, whether PI is a divisor of delta or not. Similar result for, we have the oriented Cayley graph has the desired eigenvalue form if and only if the connection set C is closed, it's a union of equivalent classes with this equivalence relation. This condition here is in fact is equivalent to the fact that -1 is not in this subgroup H delta here. And it's also equivalent for this delta being evaluated negative. So what if -1 is in H delta? So yeah, also here, what does this mean? If we consider the equivalent class that contains element G, -1 is not there to multiply G to get its negative. So its negative is not in the equivalent class. That's how we can make it. So we can make sure C and -C are disjoint, get an oriented graph. While for this case, we will have the negative is in its own equivalent class. So we will have some small Cayley graphs. Because it's indexed to the bridges in the equivalence class will break into 2 pieces. So there is a parallel result. In this case, we have a assigned Cayley graph. Let's check an example to see how does it work. So that's the information. We factor the exponent of the group. We need a character on this group to define like this. Again, these WIs can be 0 or 1, but there are restrictions on W0 and W. This W, for each delta, we have a subgroup. So here A1 equals 8. It is divisible by 8. So there is no restriction on W0 and W. All these WIs are 0. So W0, W can, each of them can take a 0 or 1. What's the delta? So it's 2 raised to W0 minus 1 raised to W. And the H delta, we are taking in multiplicative group modulo 8. We need this character evaluating the K and this Jacobian symbol of W to be 1. So this group contains exactly 4 elements, 1, 3, 5, 7. Let's just get a table of them. So our character add this Jacobian symbol. the values for this character is given here. So 1 to 7 is 1. These are -1s. For this one, as we mentioned earlier, k need to be squared for it to be 1. It's a 1 on -1 and the -1 on 3. So there's a 1 here, -1 here. Now we can get our big table. Again, we can take all the possible values of W0 at W. So 0, 0, 0, 1, 1, 0, 1, 1. So check the delta expression here. We know if there are both 0, we have a 1 here. If we W equals 1, we have a -1, 2, -2. Now we try to, the most important part is to get this subgroup of index 2 of this multiplicative group. So if it's 0, 0, now all those things matters. All the elements is inside. So it's 1, 3, 5, 7. For this case, only the value of W matters. So it corresponds to this Jacobian symbol. We take the ones evaluate at 1. So we have a 1, 5. And similar here, only this one matters. We have a 1, 7. And finally, if they are both 1, we need to take the product. So 1 and 3. This here it's the integral Cayley graph. This is our oriented Cayley. This is the signed Cayley, oriented Cayley. That's a summary of this. A1 is just the permutation matrix, like 0 map to 1, I map to I plus 1. The subscript corresponds to AI raised to that power. So we have a characterization of such oriented Cayley graphs whose eigenvalues are all integer multiple square root delta. Now we talk about the second part, its application on continuous quantum walks. If we have a Hermitian matrix, we can define a continuous quantum walk related to A. At time t, the transition matrix for this walk is given by this matrix exponential. Since A is Hermitian, we know that this transition matrix is a unitary matrix at any time. We are interested in time t such that this transition matrix have some special form. For example, if we have exactly one non-zero entry, because U is unitary, it means that the entry has modulus 1, like here. If this non-zero entry is not on the diagonal, we see there is a perfect state transfer. Just means the information transferred perfectly from one A to B. If this only non-zero entry is on the diagonal, we see the walk is periodic at this vertex A. So non-zero entries are very sparse, the most possible way. We are also interested in the other extreme case, like we check a column with this transition matrix, all of them are non-zero. But we need more. We want that column to be a flat vector, which means that all the entries have the same modulus. In this case, we see there is a local uniform mixing relative to vertex A. Yeah, so as we mentioned earlier, we define quantum walks on Hermitian matrix, but the adjacency matrix over an oriented Cayley graph is skew-symmetric. Not the Hermitian, but there is a related matrix if we multiply every number by I root of square root of -1, we do have a Hermitian matrix. And so again, that's how is it defined. It can be simplified to this one. Everything here is real. So in fact, we have an orthogonal matrix. We talked about the perfect state transfer, periodicity, and the local uniform mixing. These phenomena are related. So Chris proved if there is, we have an oriented graph. If there is a perfect state transfer or local uniform mixing involves the vertex A, then the oriented graph is periodic at vertex A. For unoriented case, only PST implies periodicity. Perfect state transfer implies periodicity. So, and the local uniform mixing is harder to study than perfect state transfer and periodicity. Furthermore, we don't have any time bound for, in unoriented case, we don't have a time bound for when if it occurs, it must be for a certain time. There is no such bound yet. For periodicity, we know if it's an integral matrix, it must happen before 2 pi for periodicity, and the uniform mixing occur before this. How are these phenomena related to integer multiple square root delta eigenvalues? So Chris and Sabrina proved that if we have an oriented graph, the work on this oriented graph is periodic at vertex A, if and only if all the eigenvalues in the support of A are integer multiple of root delta. So what is theta is the eigenvalue of X. Theta is wait, doesn't show up. So theta is in the eigenvalue support of A, mean if and only if there is an eigenvector over the matrix associated to eigenvalue theta, such that its component is not 0. For oriented Cayley graphs, all the eigenvalues are in the support of any vertex. So we would require all the eigenvalues of the graph being integer multiple of root delta. That's a characterization for periodicity. So our earlier result characterization of oriented Cayley graphs with all eigenvalues being integer multiple of root delta, it's in fact also a characterization of oriented Cayley graphs where the quantum walks on them are periodic. Before, we also mentioned in oriented graphs, for perfect state transfer to occur, the graph must be periodic. Same for local uniform mixing. So to look for graphs with perfect state transfer or uniform. So this gives us a characterization. To look for uniform mixing or other ones, we need to look inside this set of graphs. Anything outside doesn't give us perfect state transfer. Now let's see some concrete example. If we so this is the oriented for cycle. It admits uniform mixing at time pi over 4. Uniform mixing means at time t means there is a local uniform mixing with respect to each vertex at this time t. So it means that the whole matrix is flat. all the entries of this matrix have the same modulus. That's a uniform mixing. So oriented first cycle has a uniform mixing at the time over 4. And if we know how does quantum walk behave with the Cartesian product, we just have some trivial family, take a Cartesian powers over the first cycle. They all have a uniform mixing at the time pi over 4. Let's check for this example. This is an oriented Cayley graph. It also has a uniform mixing at the time pi over 4. But the important part is that it's not obtained through some Cartesian product with smaller graphs. And the underlying graph is not bipartite. We are interested in whether it's bipartite or not because there, for quantum walks on oriented graphs and bipartite graphs, there are some connection. Like if we have a bipartite graph with a local uniform mixing, we can orient the edges to get oriented graph with the uniform mixing. So this is some untrivial example not related to undirected case. This we in fact have an infinite family for this one. Now there are also some nice examples in this family for perfect state transfer. So multiple state transfer mean on this set means between any two vertices of the set, there is a time t such that there is a perfect state transfer from one vertex to another. So they can all, and then between the two. This correspond to an oriented cocktail party graph. There's a similar example. So on subset with size 4. In fact, the whole graph break into subsets of size 4 between on each subset there is a multiple state transfer. Let's check another example. So this subset only has size 3. And this is in fact oriented tournament. So we orient the complete graph on 9 vertices. All of them belong to some infinite family. And when the size of the graph goes bigger, we have some more sparse examples. Yeah, that's all I want to talk about today. Thank you.
Thank you. So, is there any question for Xiaohong?
I have just a general question. Thanks for the talk, Xiaohong. It was very good. Very interesting. So all of these things are happening on Cayley graphs and abelian groups, yeah?
Yeah.
Okay. So do you know what happens if you go to normal Cayley graphs?
I think it will just so here where over here. So here we use this subgroup of index 2. We can obtain some minimal connection set for oriented Cayley. For the non-abelian case, I think it will just be some union of these minimal classes where we need to take if G is here, we need to take all the classes correspond to its conjugate. So like HG, like this form, take all such classes too. But I only realized the non-abelian case recently. I haven't checked carefully, but I suspect